Welcome to BTEC Revision. In today's lesson, we're looking at free body diagrams, and by the end, we will be able to recall the types of forces, draw free body diagrams, and resolve forces by calculating components. Free body diagrams are diagrams that represent the forces acting on an object. They are commonly used in physics to analyze the motion of an object and to determine the net force acting on it. Here is an example of an object, and it's usually represented by a dot or a box, and the forces are represented by arrows pointing in the direction of the force. What are the forces acting on the object? Well, we're going to have the weight, which is equal to mass times gravity, mg, and we'll learn more about that in a later lesson. And there's going to be tension in these strings here. So we'll have tension in that string, and there's going to be tension in that string. To make this diagram clearer, we can draw a dot to represent the mass of the box, which is the center of mass. Then we can draw the forces. So here's our weight. Our tension in the first string we'll write as T1, and the tension in the second string is T2. Now, in the last lesson, we looked at resolving components, and we can do the same for this topic here. So for tension 1, we can break this down into vertical and horizontal components. And we can do the same for T2. Now let's take the angle between T1 and the vertical component to be angle 1, and angle from T2 to its vertical component, angle 2. How would we work out the horizontal and vertical components? Well, we're going to have to use SOHCAHTOA. Sine theta, cos theta, and tan theta. Sine theta is equal to opposite over hypotenuse. Cos theta is adjacent over hypotenuse. And tan theta is opposite over adjacent. Let's start with the tension 1 horizontal component, and that is going to be opposite the angle. There's no angle next to the tension, so that's the one we're going to use is sine theta. And if this is opposite, let's rearrange this equation for opposite, and that'll give us opposite equals hypotenuse times sine theta. And therefore, in this case, our hypotenuse is T1, so we can replace this opposite with tension 1, and then we're left with sine theta, and in this case, that's going to be sine theta 1. And we can do the same thing on the other side, but we're going to replace tension 1 with tension 2, and angle 1 with angle 2. Now, looking at the vertical components, we can see we have theta 1 and the adjacent. So we're going to have to use cos theta for that, and rearranging that for adjacent, that would give us h. And for the first tension 1, that's going to be T1 and times cos theta 1. And for T2, that's going to be T2 cos theta 2. Now, this is getting a bit messy, so we'll simplify it even further, but this time we're going to leave only the horizontal and vertical components. So we can see we have two arrows. First is tension 1 cos theta 1, and there's another arrow next to it, so we're going to add that because they're in the same direction. It's going to be tension 2 cos theta 2. The arrow going down is weight, so we'll write that as W. And for this to be in equilibrium, these two, well, three forces must be equal. So the vertical forces going up must be equal to the vertical forces going down. So we can write this as W is equal to tension 1 cos theta 1 plus tension 2 cos theta 2. And we can say the same for the horizontal components. So we can write that tension 1 sine theta 1, and over here tension 2 sine theta 2 going towards the right. There's lots more forces that you need to be aware of. For example, we know about the weight. The weight is always down towards the center of the earth. And in this case, we have a boat, and we might have an engine on the boat propelling the boat forward. So therefore, that's going to be called thrust, T for thrust. And when the boat is in motion, there's going to be an opposing force. We can have friction, and we can have, in this case, air resistance, and we can have friction between the boat and the water. And there must be another force going up because the boat is not sinking. So therefore, we can have a force on the boat going up, and it's called upthrust. Upthrust is only there when you have an object in a fluid, such as water or air. A fluid is a liquid or a gas. In this case, we have a car and it's on a road. So let's say the car is going forward. In this case, that's towards the right. So we're going to have thrust from the engine. The car also has a weight pulling it down due to gravity. And going back, we'll have friction between the road surface and the tires. And we will also have air resistance. And what is stopping the car from going into the ground? If it is on solid ground, we will have something called reaction. This is also known as the normal force. Pause the video here and attempt this exam question. In order to solve for the force F, we will need to resolve these forces into their components. So we'll start with this first force, the 20 newtons. Resolving into the vertical component, so this force going up, that's going to be equal to, using trigonometry, sine theta equals opposite over hypotenuse, and cos theta equals adjacent over hypotenuse. Remember to rearrange them for the opposite, which is h sine theta, and adjacent equals h cos theta. So we will take these values here. 20 is our h, so is 25 and 15 and f. So resolving this 20 newtons of force into the vertical, you can see that is going to be opposite the angle, because if we take this force and move it to the left, that would be a opposite. So therefore we can write this as h sine theta, which is 20 sine theta, which is 40 degrees. And for this force on the right, the vertical component, we'll write as Fv for vertical. And let's look at the vertical components going down. So we have for 25, it's a similar thing. Okay, we'll write 25 sine, and in this case, it's 45 degrees. And for the 15, it's a similar thing here. So we can add 15 sine, and in this case, that's 45 degrees. Resolving for the horizontal, we can see for the 20 Newton force. This is next to the angle, so that's adjacent, and we're going to have to use cos theta. So that will be 20 cos theta, and in this case, that's 40 degrees. And for the 25, that's 25 cos, and that's 45 degrees. And looking towards the right side, we have the force horizontal. We write that as FH. And the last one is the 15 newtons of force, which is 15 cos 45. It's equal to 15.43 newtons. Now we can look at the horizontal, and it's a similar thing here. We can see 20 cos 40 degrees plus 25 cos 45 degrees is equal to everything on the right side, which is f of h, plus 15 cos 45. Okay, so we can take this 15 cos 45 to the left, and we're left with f of h is equal to 20 cos 40 plus 25 cos 45 degrees, take away 15 cos 45. And that's equal to 22.39 newtons. So finally, let's simplify this into the force F, and resolving the components, we have the vertical, which we have to be 15.43 newtons, and we have the horizontal component, which is 22.39 newtons. So we have to resolve and solve for F. So let's have a think. What would we have to do here? If we take this force arrow, move it towards the right, you can see we have a triangle, 90 degrees. So you can just use Pythagoras' theorem here. So F squared is equal to 15.43 squared plus 22.39 squared, and then square root the answer for F, and that would give us a value of 27.19 newtons for F. And that's the end of the lesson. If you would like to boost your grades, visit us at btechrevision.com, where there is lots more resources available and lots of quiz questions. And I'll see you guys next lesson.